Welcome to class. In this video, we're going to discuss solving exponential and logarithmic equations. So how do we solve an exponential equation where the two sides of the equation are both a base raised to an exponent? Well, if the bases match, then we know that their exponents also have to be equivalent. So if you have b to the s equals b to the t, then s has to have equaled t. So when you're given an exponential equation in that format, you're going to set the two exponents equal to each other and solve. Now you may need to rearrange it. So for example, if you had 8 squared, you could write that as 2 cubed squared, which is 2 to the 6. So you can always reduce it to a smaller base if necessary in order to make the two bases match. So let's take a look at a simple example though. Let's say we have 2 to the x minus 1 equals 2 to the 2x minus 4. We can see that the bases of both exponents are the same. So we can set the exponents equal to each other. X minus 1 equals 2x minus 4. I'm going to subtract x on both sides and add 4. This gives me 3 equals x. Pretty simple, straightforward. And you can double check. 2 to the 3 minus 1 equals 2 to raised to the 2 times 3 minus 4. That's 2 to the 1 equals 2 to the 2 equals 2 to the 2. Ta-da! Now, what happens if they have unlike bases? Well, if possible, you're going to rewrite each side as a power with a common base. So that's what we were talking about a minute ago, where we could rewrite the 8 as 2 cubed. So whenever you can set them out as a common base, you can then repeat the process we just did where you set the exponents equal to one another. So in this case, for example, I have 8 to the x plus 2 equals 16 to the x plus 1. Of course, those bases do not match. However, 8 and 16 are both powers of 2. Don't be tempted to think they're both powers of 4, because even though 16 is 4 squared, 8 is not 4 to the anything. So it's not really helpful to us. So we're going to stick with 2, which is the smaller option. So 8, you happen to know is 2 cubed. And 16, you should know is 2 to the 4th. And when you raise a power to a power, you are going to multiply the exponents. So in this case, I'm going to multiply the 3 through, and here I'm going to multiply the 4 through. This becomes 2 raised to the 3x plus 6 equals 2 to the 4x plus 4. Now my two exponential sides have the same base, so I can set the the exponents equal to each other in another equation. If I subtract 3x and subtract 4 from both sides, I get that x equals 2. And of course, again, you can test this out. You can see, does it work? You can plug it in, and when you do plug it in, you get 8 to the 4th equals 16 cubed, and both of those are 4,096. Now, what if I have 2 to the 5x equals the square root of 2? Well, you're going to notice that the square root of 2 is not currently written in exponential form, so we have to rewrite it so that it is exponential. Square root of 2 can be written as 2 raised to the 1/2. Now I have two things with the same base, so I can set their exponents equal to each other. 5x equals 1/2. To solve for x, I could divide by 5, or because I'm working with fractions, multiply by 1/5. That gives me that x equals 1/10. Now, I might want to solve 3 to the x plus 1 equals -2. And I could try my hardest, but number 1, I can't find a way to make them have matching bases. Number 2, 3 raised to any power will always be a positive number because it has a horizontal asymptote at y equals 0. And so there's no way for it to equal 0 or be a negative number. If we were to graph this so that 3 to the x plus 1 was in our y1 and -2 were in our y2, we would get a graph that looks like this, where they never intersect. If they never intersect, that means there is no solution. So remember as you're doing this that no solution is always a possibility. If you have no idea how to get an answer, or you're trying really hard and you just can't figure it out, take a look at the graph. See if they even intersect at all, because they may not. Now, let's say we have an exponential equation where we can't find a common base. We're going to apply the logarithm on both sides of the equation and use the rules of logarithms to solve for the unknown. I'm going to go back for just a moment and show you this last question. And I'm going to kind of approach it that way instead of looking at the graph, so you can see another way that you would know that it has a problem. So here, if I were looking at this and I didn't have the graph, or I didn't have a way to get to a graph, I could take the natural log of both sides. So the natural log of 3 to the x plus 1 and the natural log of -2. But what you're going to notice is you can't do natural log of -2 because you can't have a negative inside a logarithm. And so that is a non-graphical way to say, oops, there's a problem there. So let's go ahead and apply these steps to a problem that is solvable. Let's say I want to solve 5 to the x plus 2 equals 4 to the x. Well, I'm going to take the natural log of both sides. Technically, you could take the plain old log, the common log, but I prefer the natural log, personally. And when I take that natural log of both sides, I'm now going to notice that I have exponents in both. So I'm going to go ahead and bring those down using power rule. I now have x plus 2 times the natural log of 5 equals x times the natural log of 4. I'm going to distribute my natural log of 5 to both my x and my 2. And I would like to get my x's to one side. So I'm going to subtract x times the natural log of 5 from both sides. Cancels here, and I have 2 natural log of 5 carries down. And then on the right side, I can pull an x out. And then I have natural log of 4 minus natural log of 5. Now you could choose to combine those logarithms into one log, because when you subtract two logarithms, you can divide their insides. Or you can just move it over as a unit inside parentheses. So you could write x equals 2 times the natural log of 5 over the natural log of 4 minus the natural log of 5. Or you could write 2 natural log of 5 over the natural log of 4/5. Depending on the problem, they might want the exact answer, at which point you would give it in one of these formats. Or they might ask you to simplify it, or not simplify, I'm sorry, round it to the nearest decimal place. So sometimes it'll be to the nearest tenth, at which point that would give us -14.4. And again, you can test this out. No reason not to test it. Always a good idea. So when you plug in -14.4 to both sides of the equation, you get approximately 2.1, 2.2 times 10 to the -9. Notice that they're not going to be perfectly exactly the same because -14.4 is a rounded value. So if you put in the unrounded value, they'll be exactly the same. So let's go ahead. I want you to try solving this by the method I just taught you. And once you've given it a try, come back and press play. So we start by taking the natural log of both sides. Then we can bring down the exponents, remembering to put x plus 1 in parentheses because it's a sum. We are going to distribute the natural log of 3. We want to subtract the natural log of 3 over, x natural log of 3. That gives me x times natural log of 2 minus the natural log of 3 equals the natural log of 3. So x equals the natural log of 3 over the natural log of 2 minus natural log of 3, or we can write this natural log of 3 over the natural log of 2/3. And if you were asked to round this to the nearest, let's say, 10th place, it would come out to be -2.7-ish. So probably best to use the approximately symbol rather than the equal symbol. Now, let's say you're given the equation in the form y equals a times e to the kt, and you want to solve for t. The first thing you need to do is get the exponential part by itself. So e to the kt needs to be by itself, so you have to get rid of the a. So divide both sides by a. Then you're going to put it into logarithmic format by taking the natural log of both sides. Remember, the natural log of e to the is going to just be the exponent. So basically you're putting in you're changing it from exponential to logarithmic format, and then you're going to solve for t by dividing by k. So let's take a look at this in practice. In this equation, I want to solve 100 equals 20 times e to the 2t for t. Notice that e to the 2t needs to be isolated in order for it to be an exponential equation in a format that's easy to switch to logarithmic. So I'm going to get rid of its coefficient by dividing by 20 on both sides. This gives me that 5 equals e to the 2t. Now that I've isolated my base to the exponent, I can put it into logarithmic form. Notice that log base e is the natural log of 5 equals 2t. So I divide both sides by t, and I get that the natural log of 5 divided by 2 is my answer. Notice that you could also write this as 1/2 times the natural log of 5, but you cannot have the divided by 2 inside the logarithm. This is not the same thing as ln of 5/2. You can actually type that in your calculator and prove to yourself that they do not match. So be very careful not to accidentally input it inside the logarithm. So on this problem, you would need to completely isolate the e to the 2x by getting rid of the 4 and the 5. Remember, you subtract before you divide. Go ahead and give that a try. Remember, isolate your e to the 2x, write in logarithmic format, and then solve for x. Do not write it as a decimal. Give it a try and be right back. So here I'm going to subtract 5 on both sides, and then I'm going to divide by 4. E to the 2x equals 7/4. Then I put that into logarithmic format. ln of 7/4 equals e to the 2x, equals 2x. Got a little e happy there. And then I'm going to divide by 2 on both sides, or in this case, because I already have a fraction, I'm going to multiply it by 1/2. Makes it just a little bit prettier. So x equals 1/2 times the natural log of 7/4. Now, let's solve e to the 2x minus e to the x equals 56. And notice that I have this title, Extraneous Solutions, which is going to give you a hint that we might have a solution that is extra and not helpful. Now you might be looking at this and say, e to the 2x minus e to the x is e to the x, right? No. So remember, when you're subtracting two things that have different exponents, you actually cannot combine them. It's not possible to do that. So this is actually going to be something called quadratic form. So what I'm going to do is I'm going to subtract 56 over. So I have e to the 2x minus e to the x minus 56 equals 0. And that should look vaguely like a quadratic to you. That's because if we say y equals e to the x, then y squared would equal e to the 2x. So you could think of this as y squared minus y minus 56 equals 0. If we think about it that way, then it makes it a little bit easier for us to figure out how to factor it. What two numbers multiply to negative 56 and add to negative 1? Hopefully you're going to factor this to be y minus 8 times y plus 7 equals 0. So you get that y equals 8 or negative 7. But remember, we're not solving for y, we're trying to solve for x. So this is where we remember that y equals e to the x. So we're really saying that e to the x equals 8 or e to the x equals negative 7. Are both of those possible? Well, in the first one, if I rewrote it in logarithmic form, I'd have x equals the natural log of 8. In the second one, I'd have x equals the natural log of negative 7. But that second one is a problem because you cannot have a negative inside a logarithm. So we have one correct solution, x equals the natural log of 8. whereas our second solution is extraneous, is extra, and is erroneous, it is not useful, we cannot keep it. So always remember to make sure that both of your answers are valid. Now, let's say that we want to use the definition of a logarithm. Well, remember, we're just going to bring up the definition again for our reminder here. Log base b of s equals c, if and only if b to the c equals s. Remember, b has to be a positive number that is not 1, and s has to be a positive number as well. You can't have a negative inside a logarithm. So in this case, what I want you to do is I want you to isolate the logarithm and then rewrite it in exponential form. Notice that when we had an exponential equation, we rewrote it as a logarithm. When we have a logarithmic equation, we're going to rewrite it as an exponential. So again, get the logarithm by itself, rewrite it as an exponential equation, and see if that gives you an answer. So here I'm going to start by subtracting 3 on both sides. 2 times the natural log of x equals 4. Then I divide by 2 on both sides because I'm not allowed to have a coefficient for my logarithm. The natural log of x equals 2. Then I can put this into exponential form. E squared equals x. So my answer is x equals e squared. Go ahead and try solving this equation for x. So I start by isolating the logarithm, which means I need to divide by 2. The natural log of 6x equals 7/2. A lot of times people now try to divide by 6. But remember, 6x is inside the logarithm. You cannot get to the 6 or the x while it is inside. Logarithm is by itself otherwise. So we're going to go ahead and rewrite it in exponential format. This is e to the 7/2 equals 6x. To get x completely by itself, I'm going to divide by 6 on both sides, which really means I'm going to multiply by 1/6 for simplicity's sake, and I get x equals 1/6 e to the 7/2. You could, of course, write this as e to the 7/2 over 6 as well. Now, I want to solve the natural log of x equals 3. I can do that by hand by simply putting into exponential format. That would be x equals e cubed. However, sometimes it's also helpful to be able to do that graphically. Or let's say you got that answer and you weren't sure if you're right. You could put y1's equation to be natural log of x, the y2 equation to be 3, and you could see where the two lines or curves intersect. And you're going to notice that the answer is going to be the intersect when x equals 20.0855, which does happen to match e cubed. So while I highly recommend doing it by hand first, you can always use the graph to double check that your work is correct. Remember, you should always show your work on the tests, so just be careful to do that. Now, let's say that you want to solve a logarithmic equation where the two sides of the equation have a log with base b. Well, log base b of s equals log base b of t works if and only if s equals t. So we have this one-to-one property that matches the one that we did with the exponential equations. So as long as the bases match, you can set the interiors equivalent. Notice that there are no coefficients in our logarithms here, so they do have to be just plain old logs. So in this case, I have the natural log of x squared equals the natural log of 2x plus 3. That means that the two logarithms have the same base. And I can set their arguments equal to one another. Now I want you to solve this quadratic and check which of the solutions, if either of them, are valid for the equation. Remember, always check your solutions for logarithmic equations. And once you've tried that, come right back. In this case, this is a quadratic equation, so I'm going to move everything to one side. I'm going to factor x minus 3 times x plus 1 equals 0, which gives me x equals 3 or negative 1. I can check each of those. When I check x equals 3, I get the natural log of 9 equals the natural log of 9. Ta-da! When I check x equals negative 1, I'm going to get the natural log of 1 equals the natural log of 1. Ta-da! So in fact, actually both equations work in this situation. Notice that I did plug my answers into the original equation, not any other variation as I went along. So that's it for this section. I hope that was helpful, and I'll see you in the next video.